Hello friends, welcome to Joy of Life. Today we are going to look at a medium level problem from Leetcode. Problem number is 221. It says maximal square. So given a m into n binary matrix filled with zeros and ones, find the largest square containing only ones and return its area. So we need to identify the largest square containing one. So here we have two answers, one being here, the other being here. So both are contributing to 4 units, and we have several single units as well present over here. Okay, so we'll see some more details. We have another example over here wherein we have only two squares consisting of ones, and they are not they cannot be connected in any way. So the answer would be 1 for each unit. So you can take either of the one, and your one would be your answer as well. So we will look at the solution. And before we look at the solution, I would highly recommend that you give it a try yourself. This is a very interesting problem. So you can just give it a go, and you can pause the video and try it yourself, and then resume the video and watch it. So we'll go to the solution. We'll look at how we can build the solution using the same input. So let's do analysis of the problem statement first. So first what I'll do is I'll quickly get the array over here. This is my input matrix, and we are going to see how we are going to come up with the solution. So in order to solve this problem, we are going to use dynamic programming. So what dynamic programming means that we will be solving all of the sub-problem while finding our answer. So what we are going to do is um, we are going to create a DP table which is very similar to our actual table that we have, and we are going to see how we are going to segregate the sub-problem and come up with the solution. So let me create the table for you first. So here I have created a table of size 5 by 4, which is having 20 cells, which is identical to our input table. So this is our input table, and this is our DP table. So DP table, what is the importance of this table? So basically each cell will answer us a problem. So let's consider this cell. What are we going to get in this cell? So this cell will tell me that how many squares can end over here, provided this is 1. So similarly, this cell will tell me how many squares can end here, provided the cell is 1. So let's say, for sake of simplicity, so let's take a small example. So let's clear this table. We can reuse this table. So let's say I have a input similar to this. So this is very straightforward. This is the maximum uh, square that we get can be of size 3. So we can get 9 square of size 1, each one of them. 9 square we can get of size 1, and what else we can get? We can get 4 squares of size 2, right? These are the 4. And we can get a single square of size 3. Sorry, 1 into size 3. So this is how it is, right? So when I have a table like this, when I have an input table like this, so we have created a DP table which is of the same dimension, right? So what this cell signifies, how many square can I create? How many squares can I create which is made out of 1 if my if my matrix is ends over here? That means my matrix is this, nothing but this. So I can create one square of size 1. Similarly, this cell will say that this is my input matrix and how many squares I can create which is ending here. The answer is 1 because we cannot consider this to be a part of this square because it's a rectangle. Similarly for this again we are answering a subproblem. This will be 1 because we cannot extend this. And similarly, going by the columns, what we'll say that using these two also you can just make 1, using these two also you can make 1. Now, when I come to this cell, what we can say that we can make a square of size 2, right? Because here, when I'm answering here, it means I am answering for this subproblem. And then over here also it's 2. That means we are answering this subproblem at the moment. Similarly, for this subproblem, we are answering over here, and then the last one we are answering for the entire subproblem, right? So DP basically solves all your subproblem, solves all subproblems. So at every stage, if you see here, at every stage we have 9 cells. We are having 9 questions that we are asking. That how many square can I create here? How many square can I create here? So on and so forth. And then we will maintain a variable which will track what is our max, what is the best we can get, at what stage we can get the best. We will deep dive into this problem with some examples as well. So before that, let's start to fill up this table. See, if I have only array of uh, element containing 1, how much I can do, how big a square I can make. I can make a square of size 1. Similarly, if it is 0, we cannot make a square ending here. A square cannot ever end here at this cell, right? Because the value is 0. So this answer will remain 0. Similarly, if it is 1, then I can create a square of size 1. That is that one itself, right? We cannot extend any of the above rows or column in order to get any better answer. So for the first row or the first column, what we do is we copy the same value from the input matrix. So this is what we are copying directly for these two cells. Okay, and now moving on to the problem. Now we come to, we start doing a normal fill up of the other cell. So when I am here, so before we fill this up, I want you to understand the problem a little in depth. So what I'll do in order to make you understand is, let me get some space over here. So let's create a simulated versions. Let's say I have a square like this and I have a square like this. Okay, so when I have two squares like this, what does that signify is all these, all of these, my values are 1, right? And definitely this value is 0. Otherwise, we would have got a square here also, right? This value is 0. So let this be my input array, right? And now let's come up with a DP table over here corresponding to this input array. So I just want you to get the idea of how we are getting the result. I don't want to talk about the pattern that we'll be looking for before you understand why we are looking at that pattern. Okay, so let's create that same table again. Um, so let's say this is my DP table. Okay, and we are answering for this cell, the one over here. Okay, so in this case, what will happen? I said we will copy the first row and column from the input table. Now, when I am here, when I'm at this cell, the cell here, what happens is I try to see that uh, what is the best I can do. So I see my diagonal is having a 0. Means there is no square at this direction. But there is a square at this direction and there is a square at this direction of size 1. So just try to visualize this problem. So when I am sitting here, I am trying to look at my top I'm looking at my left and I'm looking at my diagonal to figure out. So when I see that I cannot extend all the three, so my value is 1, so I just put 1 over here myself. So coming to the next cell, so let me clear it off because you might not be able to see it properly. Let me just remove this. Okay, I've removed too much. Yeah. So I can get a 1 over here, right? Now, when I filling this cell, I could see that in all of when I'm filling up this cell. So I see my top is having a square, my diagonal is having a square, and my left is also having one square. So what are these? What are these values? These values are nothing but the question that we have already answered. So how many square can be made here? That is the question we asked, right? And we have the answer. The answer is 1. So I can when I'm seeing that I can extend from all the three edges because my square will fit in like this. To fit in like this, I have to extend the diagonal, the top and the left. Just try to visualize that we want to extend this corner. So I have to just push it down. So not only left and down, so there is a diagonal effect as well that we have to fill it up. So I could see that I can extend one because I am taking the minimum. So there are three questions over here, right? These are the three that I have circled over here. So we'll be taking the minimum of Q1, Q2, and Q3. Plus I have my own one myself because I am also one. So my value over here would be 2. Similarly, over here also we'll do the same thing that we see that this is 1. So when I see this is 1, so I can see that I can extend all of my edges. So I get a 2 and I put this 2 over here. Now you see that we are now in a quarter wherein we have the values of 0, 1, 1, 1, 1, 2 and 1, 2, and we are trying to answer for this field. So just see this pattern that we have a square over here, we have a square over here. So I can extend this, I can extend this, but can I extend this for 2 levels? No, I can't. I can only do it for 1 level because there is a 0 on top of it. And we don't need to go and check this 0. We are getting the answer from my diagonal cell directly. So the beauty of dynamic program is that when you're first year, like for a 3 into 3 matrix, what you are doing is you are filling up your base cases first. So just let me put that base cases is filled up first, right? So I have my base cases filled up for each one of the rows, right? And each one of the column. So when I get this answer, say this one is my answer, this x is my answer. So this x is derived from this and this, right? Because we are taking the minimum of the three and considering my value to get the answer. So when I'm answering for this, I am actually checking for this, and this. When I'm answering for this, I am checking this, and this. So when I am filling up, I will only check for these values, and they have already checked for the other values previously. So when I am filling when I am filling this value, what I need to check is this and this value when I am filling up for this value over here. So I know this square can give me 1, this edge can give me 2, this edge can give me 2, but we have to take the minimum because if I take 2 and not the 1, if I don't take the minimum, if I take the maximum, I know that this edge of my square will be compromised, and we don't want that. We want all the answers to come. So that's why we do a 1 plus. We take the minimum of top element, left element, and diagonal top element in order to determine the result of this value. So here you will see how it will slowly build up. So when I have now filled up my base cases. So base cases is marked with the yellow color, and now I'll use this blue color to answer the other cases, the normal cases. So you see that this is the sub problem that I am solving for at the moment because I am sitting in this cell. So we are filling up this cell. So when I'm filling up this cell, what I do is I see that the value is 0, so I don't need to do anything. When I see a 0, I just straight away put a 0. Now I come to a 1. So I'm filling up for this value now. So when I fill up for a 1, I check the top. I see, so I check the top. I see that I can extend the top. But I see I cannot extend the diagonal or the left. So these values are compromised. So I will take the minimum of them. So minimum of these values, these three values, x, y, and z, plus my 1, because I can create a square myself of size 1. So I become only 1. Similarly, for this one also, we check the for this value also we check the top, we check the diagonal, and we check the left, and we see that we can get only 1. That is my own value. Same goes for this guy as well. Now coming to this cell, we can see that we cannot extend the top one edge, so we'll just use 1. For this guy also we can see that we cannot extend this diagonal, so we keep 1. Now we see, now I see that my for this cell, my top, my diagonal, and my left both are both are one a single unit of square like this, and my value is also 1. So if I put my value over here, I become 2, right? So 1, 1, 1. So I am taking the minimum of these three and my 1 to make it a square of size 2. So that's when I put a 2 over here. Similarly, going to the next cell, that is over here. When we check that, we see that again, I see that when I fill for this, what happens is I see that my top is a square. So I just want you to show that why we are not taking the 2. My top is a 1, one single square. My diagonal is a single square, and my left is a double square. So double square means this, right? So this is 1, this is 1, this is 2. So if I take the maximum over here and put the value, so this becomes 3. This is not a square, this is a rectangle. So had this been 2 and had this been 2, what would have happened? If this means 2 means we have 2 more over here, right? So 2 to 1 would have meant something like this, right? And if it is 2 to 2, that means this is also a square. In that case, I could have extended and made it 3. But in my case, what I see is that my top is 1, my left is 2, and my diagonal is 1. So the best I can get is a 2, and that is what we'll be will be putting there. Similarly, when the values are 0, there is no questions, we'll straight away put 0. And when I have a 1 over here, that means I have a bigger square on top and a smaller one on the left, but a diagonal left, and there is nothing on my left, so I can just have my 2. And then it's a 0, so this will be 0. So in this process, what we'll keep a track of, we'll keep a track of when we are getting the best max, and the best we got is a 2. And what we need to, so what is 2? 2 is the count of square ending there, but we need the area, so we have to do a 2 into 2, which will give me 4, and which is my final answer to the problem. So let's now look at this from the code perspective. There is nothing fancy. We are exactly going to do what we have discussed. Maybe a couple of things here and there. So, for example, one thing that I often do, if mentioned or not, is is putting a null check. That if my matrix dot length is null, then I don't need to do anything. I can straight away return a 0. Now, what we have done is we have created a DP table, right? So it's a two-dimensional table of the two-dimensional table which is having the same number of column as our input matrix. So I'll be using matrix.length and matrix 0 because they are of size m into n, so we cannot do matrix.length into matrix.length. It's not square. Okay, so I am pretty much set, and I'll store my result into result, and at the end we are going to return our result. So as we discussed that we are going to do result into result when we return our final answer. So this is nothing but result is having 2, and we are returning result into result. So result multiplied by result would be my final answer. And now what we are going to do, we are going to do a normal traversal that we do for a two-dimensional array. I'm not going to talk through it, but here you know what is happening. I'm pretty sure about it. Here, my main intention for doing this problem is to give you the idea on what I am trying to do, how I am approaching, and would like to hear if you have any doubts. I would highly encourage that you post a comment in case if you have some doubt. In many problems, what I see, I have seen a lot of dynamic problem videos where they talk about the pattern that go one step up, go two step left, get that value. But here my whole purpose is to tell you why we are doing it, why we are going one step up and one step left and one step left, and what is the rationale behind the same, why we are doing a lookup of those cell in particular, right? If you know that, then you don't have to remember any pattern that we have to go left and go one step back and get the values. So the basic intention is you realize the problem, you see the pattern, and you come up with your own solution. There is nothing to be memorized or remembered in this case. So okay, let's do so. Since we are dealing with the two-dimensional integer array. So let's convert this value to because we are getting a char array over here, which I have not noticed earlier. Anyways, what I'll do is if it is 0, so we'll just do a simple conversion. Otherwise 1. So they said it's a binary matrix, so there cannot be any other input. It could be either a 0 or a 1. So I'm just getting it converted into uh, num. And as you remember that we have filled up our base case is the one for this column and this row, right? The one marked with the yellow color. So we need to fill that up as well. So we need to copy them as is from our input matrix. So that's what we are doing, that if I is 0 or j is 0, so either I or j would be 0 if you are at the first row or the first column. In that case, what we are going to do, we are just going to simply copy from our matrix input. Um, so the base case we have already handled over here. Now we are going to handle all the non-base cases. So first thing first, we talked about num being 0. If num is 0, we are not doing anything. We are just putting a 0 on our DP table and we are moving on. So that's what we are going to do here as well. So we are just putting a DP table value to be 0 and we just do a continue. We don't need any further processing, right? And now we have to see that what is the max, what is the, I'll not say max, I'll say the min value that we are getting from those three cells that we talked about, one on the top, one at the diagonal, one at the left. So what I'm going to do is I'm going to do a math.min, and this lookup should happen at the DP table level, right? So I minus 1, I just go one level up and then I stay at the same column. I'm just looking up, nothing else from my position. Okay, and what we are going to do, we are going to check the diagonal also. So diagonal means I minus 1 and j minus 1. So one row up, one row left. That's it. And we'll get the minimum out of these two values, and we are going to uh, since we have a third value, so I have to do a math.min again. So we already have this value. We'll return this value, and what I'll do is with this with this value, I'll compare I, and I'll stay to the same row and j minus 1. So I'm just checking my previous cell, nothing else. Okay, and I am, since I am 1, because I cannot be 0, that has already been eliminated over here. I add my own self, own value 1 there, and I put this value into the dp table. dpij is equals to the main. That's the best I could get, right? And we have to continuously update our result, right? So result is initialized to 0, and we are going to store the max between the current result that we have or the value that we uh, have just computed, right? So actually, I don't need this. Why do I need to use a variable over here? Okay, and then we are going to return the result. So we are going to say result into result. That's what we are going to return. So let's run this and see. Oh, what did I do wrong? Mm-mm. We need to put the num. I have just put the char, so the ASCII value was copied. So we need to pass on the integer value, since our DP table is a uh, integer array, and the matrix was a char, so I was passing on the ASCII value of it. So we got that wrong. So yeah, our result, our code has been accepted, and let's do a submit and see for a wider test cases how it goes. Yeah, it's not bad, 4 milliseconds faster than 88.37% submission. So that's pretty good, I think. Not at all bad. So the whole intention for this program is to give you the idea on how to come up with the solution. This is, I would say, this is not a very advanced level DP problem. This is a beginner to a mid-range DP problem. The solution is pretty straightforward. You might see a lot of harder problem in the days to come. I would also try to solve a few of them and post it and share how to solve it with you guys. I hope you like the approach. I hope you got the concept. That's the most satisfactory part for me. If I was able to convey my thought process to you. So do share, do like, and subscribe if you have not done so. I always look for some kind of encouragement, and it's good that when I see that my friends and the people who are watching it are getting something out of it. So yeah, I'll keep creating more videos. Do like, share, and subscribe. Have a great day. See you soon, guys. Bye bye.